For most of human history, we categorized materials by their immediate utility. We used iron for the blades of our swords, copper for our household tools, and stone for the walls of our cities. But the primary way the ancient world organized these elements was through a merchant's lens. We looked at the brilliant yellow shine of gold, stamped it with a value, and treated it as a distinct class of object, entirely separate from a heavy, dull lump of lead. Sorting by price meant a shiny ingot and a gray rock were seen as different species. At the time, there was absolutely no standardized method to test if these substances were actually related beneath the surface. This economic view of nature began to shift in 8th century Baghdad, which had become the center of a new kind of systematic inquiry. A scientist named Jabir ibn Hayyan proposed a different metric for understanding matter. Instead of observing how elements looked on a shelf, he wanted to see how they reacted to being intentionally pushed to their physical limits. He moved the study of materials out of the marketplace and into the laboratory. By focusing on how substances behaved under heat and pressure, he replaced passive observation with active, repeatable measurement. Jabir's data came from testing 6 distinct substances: gold, silver, copper, iron, lead, and tin. On the surface, their colors and values had almost nothing in common. To find the connection between them, he subjected each one to the same set of stress tests. He started with hardness, using an iron stylus to see which materials resisted scratching and which, like lead, were soft enough to be easily marked. This diagram represents his second test, density. By weighing identical volumes of each material, he could determine the specific amount of mass packed into each substance, regardless of its outward appearance. He then tracked their thermal limits. Using intense heat, he recorded the exact point at which each solid element began to lose its rigid structure and undergo a phase change into a glowing liquid. Finally, he tested chemical reactivity. He observed how these materials interacted with other substances, such as acid reacting with copper to produce distinctive bubbles and mineral deposits. By the time the experiments were over, Jabir had stripped away the visual distractions of color and shine. He was left with a clear set of objective, physical behaviors. As Jabir reviewed his measurements, he noticed a recurring pattern. Despite their different prices and origins, these 6 materials were responding to his stress tests with remarkable consistency. Every one of them remained solid at room temperature, and every one of them could be softened by fire and bent into a new shape without losing its integrity. They also displayed malleability. When struck with a mallet, they didn't shatter like stone or pottery. Instead, they absorbed the impact, spreading thinner while staying whole. Jabir concluded that these similarities weren't a coincidence, but a scientific relationship. He stopped treating these 6 elements as isolated items and began to view them as a single collective group. He formally organized them into a specific category he simply called metals. This classification shifted the focus of study. Instead of trying to understand every element in a vacuum, researchers could now use shared data to predict how a material would behave before they ever put it in a furnace. The logic Jabir used in his 8th century workshop remains the standard for how we understand matter today. This chart is the modern evolution of that grouping system. The periodic table organizes every known element not by their appearance, but by the repeating patterns of their physical and chemical traits. We now have microscopic explanations for these traits, like metallic bonding and atomic lattices, but these are simply the underlying reasons for the same behaviors Jabir was testing with his stylus and his scales. This industrial plant is the large-scale application of those early experiments. Every beam of steel shaped here relies on the exact same rules of thermodynamics and malleability that were first recorded in Baghdad. Jabir's work demonstrated that scientific progress isn't found in looking at things, but in measuring them. It requires the willingness to ignore what is visible in order to find what is true. By setting aside the market value of gold and lead to focus on their laboratory behavior, Jabir ibn Hayyan provided the first systematic way to organize the material world.